Hello students, here is your audio PowerPoint on Module 2.3 as promised. And this is a really important chapter, and that's because if you choose to go on in psychology, you're going to continue to be exposed to this material, so it's definitely something you need to learn. It's very basic information that allows you to interpret the statistics behind the research that psychologists do. So it's called Measuring and Analyzing Results, Descriptive Statistics. And the reason why it's important to be able to interpret the statistics behind research is because statistics can be pretty misleading. So, for example, both of these graphs show the same data. However, the axes, in particular the y-axis, has been manipulated in terms of the values that it displays, and in doing that they can make the data look more or less dramatic. Here's a quick outline of what the chapter covers, or what this module covers. So we'll talk about how can researchers state the average results in a study. How can researchers describe the variations among individuals? Obviously, everybody is different, and they're going to differ on the various measures that psychologists take. And finally, how can researchers determine what the results represent something more than chance fluctuation? So are the results they get just due to chance, or are they due to the experimenter's manipulation? What researchers do is they use what are called descriptive statistics. And so descriptive statistics are mathematical summaries of results. And there are basically two major categories of descriptive statistics. One is measurements of central score, and other is measurements of variation. And there are three different ways of representing the central score. Those are the mean, the median, and the mode. And if I were in class, I would be asking, have you learned about the mean, median, and the mode before? But we'll skip that. Okay, so what the mean is the sum of all the scores divided by the total number of scores. And so you have 4 scores there. If you add them up, they equal 17, and if you divide them by 4, that's 4.5, and that would be the mean, or the average. What's important to know about the mean is that really it's most useful when the scores are normally distributed. What a normal distribution is, it's also known as a normal curve, but it's essentially a symmetrical distribution of scores that are clustered around the mean. All right, the other measurement of central score is the median, and what the median is the middle score when we arrange all the scores in order from lowest to highest. And this particular measure of central score is useful when the scores that you're working with are very abnormally distributed. So push down one end of the scale to the low end or to the high end of any given scale on a measure. So for example, if a distribution of scores is 2, 3, 5, 6, and 50, 5 is the most accurate description of the middle than the mean. Or 5 is a more accurate description of the middle than the mean, which would be 13 in this sample. So you can see the whole point of a central score is to give a description of the data. And so if you were to say that the mean was 13, it's pretty misleading in this case. And so this is because these scores are abnormally distributed, with that 50 way up on one end. And so this is an example of a case where 5 would be a more accurate description of the middle than the mean, and this is the median. So 5 is the median. And part of the reason for this is that the mean is very affected, obviously, by extreme scores, while the median is not. So the mode what the mode is the most frequent score in a distribution of scores. And for the most part, it's the least useful of the three measures of central score, except when a distribution is very abnormally distributed. So when the majority of scores are clustered at the low or the high end, or when you're working with non-numerical data such as categorical variables, like something like diagnostic classifications. This picture shows the results of an imaginary survey of the study habits at one college. And what it shows is that half of the students study very little. So half of the students study 2 hours or less per day. And half of the students study a lot, so they study from 7 to 9 hours a day. If you were to calculate the mean for these scores, it would be 4.28 hours per day, which is misleading because no one has the score of 4.28 hours per day. The median in this case is 4.5, and so that's also somewhat misleading. And so with this type of distribution, which is called a bimodal distribution, which has two common scores, or two very common scores, which are 0 and 8, this type of distribution would best be described as a bimodal distribution, and you would report the modes, which would be 0 and 8. Here's a figure that represents the differences between the median, the mean, and the mode, and it does so by showing you the monthly salaries of 25 employees of a made-up company. And so you can see that most people in the company earn somewhere around $2,000 a month. One person is right at the median, so there are 12 people earning more than this person and 12 people earning less. That person earns $3,000 a month. And then you can see the way up there is the mean at $5,700 a month. And it's just a way to show you how affected the mean is by the really extreme score of the one person who earns $45,000 a month. So the mean is affected by that, whereas the median and the mode are not. And it's part of understanding, what is the appropriate descriptive statistic to report when you're reporting on your research. Okay, so go ahead and calculate the mean, median, and mode for this distribution of scores. If you do that, you'll find that the mean is 5, the median is 4, and the mode is 4. Okay, here's another iClicker question. That's something you can test yourself with. Another iClicker question. Okay, the next thing that we're going to talk about, so we talked about there are two broad categories of descriptive statistics. So first we talked about the central score and the mean, the median, and the mode. Now we're going to move on to talk about measurements of variation. And it's very important to measure the variation in the data that you collect, and that's because individuals can vary very substantially on their performance on any given test. And so one measure of variation is called the range, and the range is essentially the distance between the highest and the lowest scores in a sample. So for example, if our distribution has the scores of 1, 2, 3, 5, 7, 9, 9, 10, the range is from 1 to 10. The range is actually obviously a pretty simple measure of variation in the data, and it's not particularly useful because it only reflects the extreme measurements. Another measurement which is more useful is called the standard deviation, and the standard deviation is a measurement of the amount of variation amongst scores in a distribution. Here are two different distributions of scores. Interestingly, these two different distributions have the same mean, but but you can also see that they have different variances and different ranges. Okay, so one score is going to or one distribution is ranging all the way down from 38 to 100. The other only goes from 56 to 94 or so. So even though they have a different mean, they have different variances. So you can see there's a much broader range in the first sample compared to the second. And so as a consequence, these are also going to have different standard deviations. So the way it works is the more closely the scores are clustered around the mean, the smaller the standard deviation is. And when the scores are more widely distributed, the standard deviation is larger. And so you don't need to know the calculation for standard deviation. What you need to know is that, let's go back to the previous picture, when the scores are more tightly clustered around the mean, like in sample B in this picture, then the standard deviation is going to be smaller compared to when there's a much larger variation amongst the scores in A, which will have a large standard deviation. Something else to be aware of is that standard deviation is a type of measure that is useful for making comparisons on different tests or on different versions of the same tests. So for example, if you scored one standard deviation above the mean on the SAT, you would likely score about one standard deviation above the mean on the ACT. And in this figure you can see how SAT can be expressed in terms of standard deviation, so you can see the conversion of the scores into standard deviations. So if you score between 400 and 600 on the SAT, that would be within one standard deviation of the mean. And part of this has to do with that this test was specifically designed for the mean to be at 500 and for there to be a normal distribution around that mean, and that is part of what allows it to be converted into standard deviations and then hence allow the comparison between different tests. Okay, so now we are going to move on and talk about evaluating results. And so, we're rarely certain in the world of research, and so we have to what we have to do is make what are called inferences. And so to infer is basically to guess based on the evidence. And inferential statistics are the mathematical procedures we use for making these types of educated guesses. And I believe I mentioned in class the other day that because it's so difficult to study really large populations, statements about large populations are generally based on an inference that's made from a much smaller sample. Basically, what the importance of inferential statistics is that they help us determine how seriously we should take the results of a study. And more specifically, they help us determine the probability that purely chance variation would result in a difference as large as the difference you find in a particular study. And you've probably heard about one type of inferential statistic, which is called a probability value, or also known as a p-value. So a probability value basically estimates how rare a given score would be in a sample based on what's known about the likely range of scores in which the population mean falls. So for example, if a researcher says that there is a 95% certainty that the population mean falls between 5 and 7, and a particular score falls at 8.2, then that score has a probability value of less than 5%, and that's expressed as p is less than 0.05, and this would be considered an exceptional score, so not due to chance. And basically that's how exceptional scores are often interpreted, is as that they are unlikely to have arisen by chance. And a result that's unlikely to have occurred by chance is interpreted as being statistically reliable or statistically significant. So something else to know about statistical significance is it depends on three main factors. So the size of the difference that you find between groups, the number of participants in each group, and how much the individuals vary. And the way it works is the smaller the p-value, the more impressive the result. So a p-value of less than 0.01 is more impressive than a p-value than of p less than 0.05. So what happens if we don't find statistically significant results? Basically what you do is you just, lose a little bit of confidence in the hypothesis and the results of the study. And, you also look for replication. And if researchers continue to find a lack of statistical significance in whatever type of study they're doing, then you should be more and more skeptical. Some scientists say that in addition to, and even some journals recommend that in addition to reporting the p-value, that you report the means and 95, what's known as the 95% confidence intervals. The 95% confidence interval is the range within which the true population mean lies with 95% certainty. And so essentially what we do is we infer where the true mean of the population of interest lies based on the sample mean. And we use a confidence interval to reflect how sure we are that the mean lies within a certain range. The calculation of the range or width of the confidence interval is based on two things, the sample size and the standard deviation. So here's an example of a statement that a researcher might make. I already made this earlier, but we're going to look at it now with confidence intervals. So based on an analysis of this sample, I am 95% confident that the true population mean lies between 5 and 7. And, different journals have different requirements. If they're asking for confidence intervals, they're typically reported at 90%, 95%, or 99%. What you need to be aware of is that if the standard deviation is small in a sample on which the confidence interval is based, then you can increase your certainty without having to broaden the size of the interval. So you're looking at confidence intervals in this figure here. Those are what those funny little white bars are. And these particular vertical lines shown in the two different figures A and B indicate the 95% confidence intervals. The pair of graphs essentially indicate that the two means have a 95% chance of falling in a really narrow range in sample A, and that's reflected by the smaller bars, and it has a 95% chance of falling in a much wider range in sample B, and you can see that because of the larger bars. And so you can essentially assume that in A, the sample size was large and the standard deviation was small, and then the true mean is very likely very close to the population mean. And then in B, basically the sample means are almost more like rough estimates because of how wide the confidence interval is. All right, so last but not least, there's just a couple of concluding statements. I'll let you guys go ahead and read that on your own, and you can let me know next week whether it works for you to be able to listen to the lecture. I'm hoping that by being able to stop and start, if there's something you don't understand, that will be helpful. Okay, thanks.